The rapid development of technology in the field of new and renewable energy has an impact on the high demand for energy storage. Energy-based mobile devices such as a smart grid cell phone are enhancing the development of lithium-ion batteries, fuel cells, and supercapacitor, which has great potential in electrification of large-scale energy transport and storage. Electrochemical-based energy storage is a solution for the availability of clean and sustainable energy. The Indonesian government pays a great attention to development of electrochemical-based energy storage industry, especially lithium-ion battery. One of the important components in lithium-ion battery is a separator. Separators are used to prevent short circuit between two electrodes. The separator must have a thin thickness and high porosity, electrolyte absorption and retention, as well as good thermal stability. Separator fabrication generally use toxic material and goes against the concept of environment, low carbon, and sustainable development. Based on this, renewable polymers such as cellulose, polyvinyl alcohol as an alternative to polypropylene and polypropylene are of concern. Cellulose is a natural resource that is very abundant in nature and plays an important role as a constituent of plant cell walls. In general, cellulose can be obtained from various biomass sources, one of which is alga. Serangan Island, located in Denpasar City, is an area that is used as a center of seaweed cultivation and turtle conservation in Bali. The island is very potential for alga because as much as 20% of the harvested seaweed, Eucheuma cottonii, is washed. Based on the abundant and poorly utilized alga wealth, researchers will explore the potential of Eucheuma cottonii cellulose found on the island of Serangan, Bali as a separator in lithium-ion batteries. In general, the manufacture of cellulose-based membrane separator can be done using the solution casting method.
The manufacture of Cellbrator as a membrane separator for lithium-ion batteries from cellulose algae Eucheuma cottonii using printing or casting technique. And this is the result of Cellbrator. Cellbrator has a smooth and thin white colors. This indicates that physically, Cellbrator has entered the existing polymer-based membrane separator, and also the thickness of Cellbrator is 40 micrometers. As you can see on the slide, this is the GA graph on Cellbrator. We can see the cellulose separator membrane undergoes decomposition at temperature of 350 degrees Celsius. The test result showing us that the cellulose membrane was able to absorb liquid electrolyte quickly when it is dropped on the membrane surfaces. And also this means that cellulose membrane is suitable for use as a battery separator because it can increase the wettability properties of electrolyte. The cellulose membrane changes colors from white to transparent due to electrolyte absorption. However, after 72 hours of observation, there was no change in the dimension or geometry of the cellulose membrane. This is XRD test result on cellulose Eucheuma cottonii. According to the XRD defector graph, the cellulose extract of Eucheuma cottonii had the highest peak that appeared at angle of 2 theta equals 22.4 degrees. This means that the structure of the cellulose with a distance of 0.9H339 angstrom with a crystallinity index of 82.13% and the degree of crystallinity of 84.21%. This is Cellbrator electrical conductivity graph. The electric conductivity graph shows a linear line as a function of frequency following the phenomenon of AC conductivity. The electrical conductivity of separator as measured by LCR meters is 63.8 at a frequency of 1000 kHz. So this means that the Cellbrator have a good conductivity.